So good afternoon. My name is Pekka Sinervo, and I have the pleasure of introducing our speaker, Mark Chen. Mark is actually currently the Gordon and Patricia Gray Chair at Queen's University. He has been one of Canada's sort of leading astroparticle physicists, working primarily underground. He actually did his doctorate at Caltech, then was a assistant professor there for a few years before he then came to Queen's University, joined the SNO experiment in 2000, was involved in the very first papers that now have amassed something like about 10,000 citations that demonstrated that neutrinos have mass. He then subsequently became sort of the intellectual lead of the follow-on experiment called SNO+, where instead of focusing on the search for or study of solar neutrinos, which it can do and has done, its real purpose has been to study neutrinoless or search for neutrinoless double beta decay. It's a challenging experiment, which he has been the lead on now for well over a decade, and they are moving closer and closer toward that. He's been recognized in a number of ways. Besides the endowed chair he holds, he's won the Premier's Research Excellence Award. He's won Polanyi Award, a number of other recognitions. So it's really delightful to have him here, giving you an update on the most recent work from SNO+. So perhaps join me in welcoming Mark.
Thanks very much. And can you hear me okay? The microphone's working all right? Great. Well, thank you, Pekka, for that nice introduction. And thank you to Ziqing also for inviting me. It's always nice to come here. So today I'm going to talk to you about geoneutrinos. And before I launch into that, let me just ask, are any of you geoscientists from Earth Sciences? Great. Okay, good. So if I have any questions, I'll ask you about them. Okay, because it's a fun and interesting field where we're trying to use our neutrino detectors to uncover some things that about the Earth that only neutrinos can provide, and so I hope to be able to share with you our latest results on geoneutrinos detected by SNO+. In fact, these results we're submitting to the archive tomorrow, so you get to see them. You're the first to see them outside of the SNO+ collaboration. And here we go. So neutrinos from the ground up. I think I should start with just an overview of neutrinos, just to make sure that we get the basics covered. So neutrinos are leptons. They're the neutral charge leptons, the partners of the charged electrons like electrons, muons, and tau particles. Being neutral charged and then being leptons, neutrinos only interact by the weak nuclear force. Right, so their neutrinos are produced or absorbed or scattered only via the weak interaction, which makes them then very difficult to detect. And as a result, neutrinos for decades have been challenging particle to study within the pantheon of particles that exist in the Standard Model. And it wasn't until 1998 and 2001, 2002 that we discovered that neutrinos aren't massless particles. Okay, so then the Standard Model was built with neutrinos as massless fermions, massless particles. But then the discovery of neutrino oscillations by the Super K experiment and by SNO revealed that neutrinos have a finite mass. It's tiny, but it's finite. And as everybody knows, this was recognized by the 2015 Nobel Prize that was shared by Art McDonald at Queen's. So what are neutrino oscillations? There we go. Neutrino oscillations are quantum mechanical phenomenon. It is the quantum mixing between the flavor eigenstates of the weak interaction and the neutrino mass eigenstates. And I'm teaching Introduction to Quantum and Relativity this year. And so I was just showing students the two-slit interference in my class yesterday. And so neutrino oscillations are very much like the two-slit interference that occurs for light, occurs for electrons, right? For matter waves as well as for light. So how do neutrino oscillations work? And speaking very generally, so when a neutrino is emitted as a flavor state by the weak interaction, then the flavor state is a mixture of the mass eigenstates. So then there's a mixing matrix here that then has been expanded into numerous sort of sub-matrices. But if you multiply all together, you have a 3x3 mixing matrix that then tells you that each flavor state is composed of different mass eigenstates. Okay, and so then those mass eigenstates will propagate with a different phase relationship. That's just quantum mechanics and the Hamiltonian, the propagation. So when the phases don't align, then you don't detect the original flavor of neutrino that was produced until they line up again somewhere down the path of propagation, so in L or in T. So then you get an oscillatory pattern, right? What happens is that the neutrino masses are different, and so then it introduces a different phase in their propagation. And why is this like the two-slit interference? So when the neutrino is emitted, say, as an electron neutrino, then we don't know which of the mass eigenstates was emitted. Okay, so if you don't know which one it was emitted emitted as all of them, right? In a quantum mechanical mixing, just like light is passing through the two-slit, and if you don't detect which slit it passes through, it's passing through both, so then the light interferes with itself. And that's what neutrino oscillations is that the neutrino is interfering with itself. Its own mass states are interfering with itself, introducing an oscillatory pattern for the detection of the flavor. Okay, so in the quasi-colloquial way, that's a way you can picture neutrino oscillations. And so in the past 2 decades, since their discovery, then neutrino experiments have been studying neutrinos at accelerators, the atmospheric neutrinos, at reactors, studying through solar neutrinos, the mixing parameters. And in fact, all of these mixing parameters, apart from just the one here, have been measured with some decent precision. And then this entire sub-matrix of the Majorana phases is to be explored. We may never explore those parameters, but they're insignificant in terms of actual neutrino oscillations. And so the open questions that remain in neutrino physics include, we know neutrinos have a finite mass, but I don't know the absolute mass scale. Right? So if there are 3 mass states of neutrinos, we don't know what is the mass of the lightest state. There are limits for the sum of the neutrino masses that come from cosmology. There are measurements of the mass splittings, these delta M squared values between the different mass states. These come from the oscillation experiments. But we don't know of these 3 different mass states what the ordering is, whether the state that is the most electron-like flavor is the lightest, or whether it's heavier and the state that's the least electron flavor is the lightest. So this was called an inverted ordering, this one called a normal ordering. And this pattern of the neutrino mixing and the delta M squared, the mass splitting between the neutrino states, these have been measured by oscillation experiments since the discovery, so meaning in the past 2 decades. The mixing angles, right, have also been measured. There are 3 mixing angles that we call theta 2,3, theta 1,3, and theta 1,2 that describe the mixing between the mass states and the flavor states. But the absolute mass scale has not been determined. And that's an outstanding question in neutrino physics. The mass ordering, which of these 2 is still to be fully resolved. Whether there's CP violation in the lepton sector depends on whether this phase, called delta CP, whether this phase is non-zero or non-zero and pi and 2 pi. So whether that exists here. And then finally, the fact that neutrinos have mass is an observation of physics beyond the standard model, right? So how do neutrinos acquire their mass? What's the mechanism for that? It could be that we write down Dirac mass terms in the Lagrangian, and neutrinos are very much like the charged leptons and how they acquire their mass through Yukawa coupling to the Higgs. But then there are a lot of things that don't really work, because then it requires a right-handed chiral neutrino state that then is a sterile neutrino. But it could be that they're Dirac in nature, or they could be Majorana, in which case neutrinos are their own antiparticle. This question about whether neutrinos are Dirac or Majorana is a fundamental question in neutrino physics, the origin of neutrino mass. It's what the goal of the neutrinoless double beta decay experiments is in order that those experiments attempt to detect neutrinoless double beta decay, which would prove that neutrinos are Majorana particles. And that would be the subject of an entirely different talk that I would be giving you. But then, if you forgive me for the very quick overview of neutrino physics, we study neutrinos because we want to understand the properties of this fascinating particle. But we also study neutrinos, or build neutrino detectors, to use neutrinos as a probe of the sources that are producing them. So we can detect solar neutrinos, and then from those neutrinos, learn something about the reactions that are taking place that are producing those neutrinos in the sun. We can see the neutrinos that are emitted by the Earth, and that's the subject of this talk. I'll talk about the geoneutrinos. There are efforts to use neutrinos to monitor nuclear reactors. And if we're fortunate to have another supernova go off in our vicinity, in our cosmic vicinity, then by detecting those neutrinos from the burst of neutrinos released by a core collapse supernova, then we possibly can learn something about the mechanism behind the supernova core collapse. Okay, but then I'll tell you about the geoneutrinos and introduce this also from the basics. Okay, so what are the geoneutrinos? Okay, so in the Earth are naturally occurring radioactive elements, such as uranium and thorium, also potassium. And these are long-lived radioactivities, right? So uranium and thorium have half-lives of 10 to the 9, 10 to the 10 years. Similarly, for potassium, 40, one of the isotopes of potassium. So present in the Earth is natural radioactivity, and then the decay of those elements, these naturally occurring radioactive elements, generates heat. Right? So those are undergoing beta decay for the most part. There's alpha decay also from the uranium and thorium decay chains. And it's thought that uranium, thorium, and potassium, the sum of those, account for over 99% of Earth's radiogenic heat production. So there's some quantity of radioactivity in the Earth that's an ongoing decay that produces heat. And if we can figure out how much uranium, thorium, potassium is in the Earth, that would cover 99%. You know, geoscientists believe that would cover 99% of Earth's radiogenic heat. And of that quantity, the amount of heat that's produced by radioactivity, that's thought to be a fairly large fraction of Earth's total heat flow, something as large as maybe 40%. But these are rather uncertain quantities. Potassium-40 itself could be 20%, thought to be 20% of the radiogenic heat of the sum of those three. And so then let's just look again at these decays so we can understand them a little bit better. So uranium and thorium exist as decay chains, right? So U-238 will decay by alpha decay, but then you get a series of alpha and beta decays that then end up with a stable lead-206. And the thorium-232 has a decay chain that ends up with stable lead as well. And in these decays, you have alpha decays, but also you have several places where you have beta decays, right? And so in a nuclear beta decay, beta minus decay, what happens is a neutron turns into a proton, and out comes an electron, a beta minus particle, and then you get a nu-E bar, and an electron-flavored antineutrino is emitted. And so in heavy elements, which are neutron rich, we could expect you could have some isotopes. And then within these decay chains, we see there are isotopes that undergo beta decay. So they're emitting a new E bar. And so then within the Earth, Earth is a source of electron antineutrinos. Those are the geoneutrinos that we're going to try to detect and that we have detected now. So then we can directly relate the flux of these geoneutrinos to the total amount of heat that's produced per decay. And then if you can then measure the number of geoneutrinos, you're basically measuring how much heat is produced by all the uranium, all the thorium that's in the Earth is the goal, okay? Let's take a look at the potassium decay just to clean up this story here. Potassium-40, this decay goes both ways, right? It beta minus decays with a 90% branch, right? And so then this is emitting a new E bar in the same way. It's a beta minus decay. Potassium-40 also electron captures with a 10% branch. So this excited state for us, those of us who do low background experiments, this is a source of background in our experiments where we see this gamma ray, that 1.46 MeV gamma ray, potassium-40. But these are inconsequential as far as radiogenic heat production in the Earth, because this is a small branch and the energy that is small for this. It's inconsequential in the field of geoneutrinos. It's not inconsequential to the actual production. When one's quantifying the amount of heat that's produced by potassium decay in the Earth, and then the fact that it decays both ways is included, right? Potassium-40 is just 1 part in 10 to the 4 of all potassium on Earth, but Earth is abundant in potassium, right? So there's plenty of potassium-40 on the Earth as well. And then these are the 3 sources of the geoneutrinos that we can think about. Okay, so what are the questions in geoscience that are related to geoneutrinos? In other words, how could measuring the geoneutrinos help shed some light on some of these questions in geosciences? So let's go through these sort of category by category. Okay, so the simplest question is, what's the total amount of heat that's produced by the radioactive isotopes in the Earth? What's their contribution to Earth's heat flow? And the observation here is important, is that seismology tells us a lot about the Earth, right? But seismology tells us about density and the structure of the Earth, but it doesn't tell us about chemical composition, not directly at least, right? So neutrinos might be the only way. I think geoneutrinos can probe these questions, right? Again, the goal is to assay the whole Earth by looking at Earth's neutrino glow. And these questions are important in terms of models of Earth's energetics. For example, there's a quantity called the Urey ratio, which is just a ratio of how much heat is generated in the Earth or in the mantle, for example, compared to the amount of heat that's lost. And then this figures into models for mantle convection. The mantle convection is important for plate tectonics, for volcanism, and just understanding Earth's thermal history, how the Earth evolved over the span of geologic time. The radiogenic heat-producing elements, these HPEs, they play an important role. And so then by measuring the geoneutrinos now, we can provide some information that we hope the geoscientists will be able to relate to and uncover some additional information. So about Earth's heat flow. So what gets measured is there are boreholes where the temperature gradient is measured in a borehole. So, a field geologist will go through and then, drill a borehole and sink a series of temperature probes to measure what the temperature gradient is. From that, you can measure the Q dot, right, the heat flow. And then this is sort of an image of what that looks like crudely, is that, coming through the top of the Earth, out the top of the Earth is something like integrated over the Earth's surface, 47 terawatts is what's been quantified by Earth sciences. And there's going to be some flux from the core to the mantle. And then there's some production of heat as well inside of these different layers in the lithosphere or the crust in the mantle, thought not to be so much in the core. And so then the breakdown, and a figure from Bill McDonough, who has studied Earth bulk chemical composition, a breakdown of Earth's the terms that contribute to Earth's heat flow include these two pie segments, right? The amount of heat that's produced by radioactivity in the mantle, the amount of heat that's produced in the crust. This is the heat that's the heat flow from the core to the mantle. This term is called secular cooling. That's just the leftover heat from the formation of the Earth. Okay, so then how much of the heat that's coming out of the Earth now is from the original fact that the Earth was very hot when it was formed. And then only small term that comes from tidal dissipation and chemical differentiation in the core and mantle. Okay, so perhaps geoneutrinos can probe this question: how much radiogenic heat, and contribute in that for that type of to that question. Next category of questions, right? Are the fundamental ideas about Earth's origin and thus its bulk chemical composition correct? Are the basic models of the composition of the crust correct? And here I would say geoneutrinos can try to test which ones of these are correct. Okay. So let's look at Earth's bulk chemical composition. And here's a super interesting observation. All right, so we can do spectroscopy of the solar surface. And from that, we can measure the elemental abundance at the solar surface. And we can plot that for all these different elements here. And here, that's going to be normalized to silicon at this value, 1 times 10 to the 6th. Okay. Then there's a class of meteorites, the CI carbonaceous chondrites. Okay, so meteorites that have fallen to the Earth, been recovered, and then the elemental analysis is done of these meteorites. And if you plot them and normalize the elemental abundance in these CI chondrites to silicon, then this is a beautiful line, right? Which explains, apart from these very light elements that are outliers for perhaps reasons that you could guess, related to stellar nucleosynthesis, then this is telling us that this type of material, these chondritic meteorites, they represent the primordial material of the solar system. Right? So then this material has fallen to the sun and is accumulated, and the sun is the most abundant mass source in our solar system. And so if this is the distribution of the elements of the solar surface, and then these are the meteorites that have the same distribution, this is maybe the base unit that we can use to build up the Earth. Okay, and so then the model looks like this. Here's my very simple PowerPoint animation. Okay, so we have these meteorites floating around in the early solar system, right? And so then they coalesce, right, to become the rocky planets. And then when they coalesce, then what happens is there is a differentiation initially between the rock and then the metal, right? So the metal being the iron core that falls to the center, accumulates in the center. And so then this primitive mantle, if you exclude the metal, if we believe this model that the carbonaceous chondrites represents the primordial material of the Earth, that form the Earth, then we can analyze those chondritic meteorites and then determine what the models would then have a prediction for how much the elemental composition would be in the bulk Earth, right? The Earth then is not cooperative. It doesn't look as simple as this, because later it undergoes differentiation through convective processes in the mantle and geochemistry of the rock, and ends up actually enriching the upper layers with uranium and thorium, for example. So then, for example, a continental crust rock is like ppm quantity of uranium, but then lower in the crust, we find it's a smaller quantity. The ocean crust is even less. And then very rare samples from the upper mantle have even less ppb quantities. Okay, so there are processes, chemical processes that then differentiate. That's a problem, right? That's why we actually don't know what's deep inside the Earth, because most of our samples of rocks are from the surface, right? But if this model is correct, then that by assaying the whole Earth and trying to determine the uranium thorium, then maybe we have a way to figure this out. Okay, so then that becomes the Earth, and Yeah, so continuing along this, I won't spend too much time on this. Then there are elements that are classified as refractory. That means these elements like to be in the melt. These elements are called lithophile, right? So lithophile means rock loving. So you have some elements that like to be with the iron that's in the core and others that like to be in the rock. And then if you again plot this now normalized to magnesium and then relative to the Ci chondrites, then you find a whole bunch of elements land in this category here. Again, a slide by Bill, who's been one of these leading proponents in this subfield of geoneutrinos from the earth sciences community. Okay, so then uranium, thorium show up here. They show up here in this refractory. So then, Bill tells me that if I tell him how much uranium, thorium is in the earth, he says, I know all these elements too, is what he would say, right? And then, but these ones you wouldn't be so certain about because they're moderately volatile. They could be lost to space during the early formation of the earth at high temperatures. And so, but it's interesting that there's a way to tie not just, so if you measure uranium, thorium, that's great, but maybe there's a way to tie that to other elemental abundances in determining Earth's bulk chemical composition. Okay, so continuing on that, so then these models are called bulk silicate Earth, BSE, and then there are different kinds of bulk silicate Earth models, and in them we're going to, because we're neutrino people, we're going to categorize them into 3 different ranges of how much heat they produce from the radioactivity. In other words, these have less uranium, thorium, and these would have more. So then there's a class of models that are called cosmochemical because they're based on isotope geochemistry of meteorites. There's a class of models called geochemical because they're based on elemental composition of meteorites. And then there's other models that are actually geophysics, right? Not geochemistry, but geophysics. They're based on if we see mantle convection and understand how much heat, how much energy we need in that process, we can figure out how much radioactivity I need to. And so we can, from the physics side, they can say, well, I think you need this much radioactivity. So we'll call these geodynamical or geophysical models, okay? And then there's questions, where is that radioactivity distributed? Here's a cartoon of the core, and you can imagine putting in layers of material in the mantle, either deep in the earth, so right at the core mantle boundary, or distributed in 2 different layers, or maybe it's homogeneous. Okay, so those are questions that are open questions, interesting ones in the geoscience community. And then, not to beat this to the bitter end here, but these models that we saw, they continue to be developed and studied. So for example, here's a recent talk by Paul Froissart, and notes that in doing isotope geochemistry of neodymium-142 versus samarium, the observation is that for these different types of meteorites, the isotopic ratio in this system is different than what's seen on Earth. And then this is very relevant in terms of estimating Earth's bulk composition, including the amount of uranium and thorium. So this is a long story, and I haven't even touched on how to explain this properly to you. But models where we have low amounts of heat or medium amounts of heat or high amounts of heat produced by the radioactive elements in the Earth, from this neodymium isotope analysis, then Boyer and Froissart would predict this amount of heat produced in the Earth. So these are actively being developed. How do we hear about these types of models? So for example, 2 weeks ago, I hosted Neutrino Geoscience 2025 in Kingston. It's a conference series where we bring neutrino people together with the geology geoscientists. And we ran this tiny little workshop, but a productive one, where we got to have these interactions with geoscientists so they could hear what neutrino physicists can do for them, and we can hear what are the interesting questions that they are doing. Okay, so it's a plug, but it's too late for me to plug this. This already happened. Okay, so, but it turned out to be an excellent workshop, and we had fun in Kingston. Okay, so then we're down here, right? That geoneutrinos can possibly attempt to test these models of Earth's composition and possibly Earth's origin, right? Final question, where are these elements located in the deep Earth and the mantle? Is it homogeneous or is it layered? So that cartoon figure already hinted at that. Is there any lateral variability? Mantle plumes are an obvious example of lateral variability that we see. Evidence on Earth, such as the Hawaiian chain of islands and the volcanic activity, could be from a mantle plume that could come all the way from the core mantle boundary, right? Neutrinos might be able to probe this someday. Additional questions: is there any radiogenic elements in the core? In particular, did potassium fall into the core? Is an open question. This is the subject of a whole other talk I could give you on the potassium 4D geoneutrinos, but we'll have to leave that. So just to give you a picture of what this lateral variability is in the deep Earth. So here's a global map, and it's a map that shows the rate of geoneutrinos. Okay, so then we only just got introduced to geoneutrinos. We'll see more in upcoming slides what it is we're talking about. But if we can detect these neutrinos from uranium and thorium decay in the Earth, then this is a calculation of what your rate would be. The rates have this unit. One, they're called TNU, terrestrial neutrino unit, patterned after the SNU, the SNUs, or solar neutrino units in the old days of solar neutrino research. And so a TNU would be one event per 10 to the 32 protons in your target per year, assuming 100% detection efficiency. And why this number 10 to the 32? It's roughly 1 kiloton of CH2 liquid scintillator. Liquid scintillator, organic liquid, has approximately CH2 in composition. So if you imagine a kiloton of that, you would have 10 to the 32 protons. So then it's how many events you would have per kiloton per year. And these are numbers that are, say, in the tens. And you can see it varies across the Earth. So what we're seeing here is actually the variability due to the thickness of the crust. Okay, so where the crust is thick, like in the Himalayas or other mountain chains, then the thicker crust has more uranium thorium, because we actually saw that the crust gets enriched in uranium and thorium by geochemical processes during mantle convection. Okay, and then other places the rate is small because the crust is thin, and the ocean crust doesn't have very much uranium and thorium. So, well, there's that. So then where you are on the Earth will determine will give you some variability in terms of the signal you see, because the crust introduces that. But then if you can imagine making measurements, say, in the ocean, you could see there's also possibly variability, and this is in the deep Earth now, that in the mantle, seismology reveals there are these regions that are called LLSVPs, okay, large, low shear velocity provinces, they're called. Okay? So then any geoscientists here, if anybody has any questions, I have to ask you what those are, right? But seismology reveals these, but we don't know the composition again, right? We know the seismic behavior of waves going through. These have low shear velocity, okay? And they're extensive. And then if you make a hypothesis that there are thermochemical piles, and then some hypothesis about the composition of these zones, you could have variations of the geoneutrino rates that are due to heterogeneity in the mantle, right? So the assumption is the mantle underneath the crust. This previous slide showed us that, oh, it's where you are, there's variability because the crust is different. And this is telling us maybe underneath in the deep Earth is also different. So then those are some of the things that those are some of the things that we in the neutrino community can try to investigate with our geoneutrino detectors, okay? So then how do you detect a geoneutrino? So far, we've been using large liquid scintillator detectors for this process. And it looks something like this. This is a figure that comes out of this book, Treatise on Geochemistry. I am an author in this book of this chapter on geoneutrinos. If you want to order this book on Amazon, it's $10,000. Yeah, pretty rare book, right? But it's actually it's a library reference in the field of geochemistry. And so in geoneutrinos, then what happens is you have a nu bar. Okay, so that's the geoneutrino emitted by uranium and thorium decay in the Earth. And then that interacts with a proton in your liquid scintillator, or hydrogen in liquid scintillator. And then you get this reaction that we call inverse beta decay. right? Nu E bar proton gives a positron. This will give a flash of scintillation light. The proton turns into a neutron. The neutron thermalizes and it walks a bit in your detector, and then it finds another hydrogen. And then the neutron captured gamma is 2.2 MeV. This makes a second scintillation, right? So you have a prompt event and a delayed event. A coincidence event that lets you tag this event and say, oh yeah, I saw an anti-electron neutrino interact in my detector. Okay. Helps you discriminate against backgrounds. Also helps you discriminate between solar neutrinos, which are just nu E, right? They just scatter off of electrons. This produces the delay coincidence signal, so you know it's a nu E bar, okay? Possibly from the Earth. Okay, so then the characteristics of the IBD reaction, inverse beta decay, it's got a respectable cross-section for neutrinos. The energy threshold is 1.8 MeV. So as a consequence, the endpoint for potassium-40 is 1.3 MeV. So we can't see the potassium geoneutrinos, even if it's important in terms of geoscience to understand how much potassium is in the Earth versus uranium and thorium. Our detectors can't see that, but there's a whole other talk I can give you about trying to detect the potassium-40 geoneutrinos. Okay, so then above this threshold, though, you do see that U-238 and thorium-232 produce neutrinos above that threshold. U-235 exists too with some smaller isotopic abundance in the present-day Earth, right? But the nu E bar from U-235 is below this threshold, so it's just uranium and thorium that we can address. And then I already told you get a delay coincidence signal. The mean capture time is about 200 microseconds, so it's a good delta T that you can use to tag these events and really suppresses backgrounds. So that's what we do. And then so it's just this branch, right, of the neutrinos. This is the neutrino energy spectrum that's produced. And then if you then fold the spectrum times the cross section that increases with energy, then this is the rate that you see in your detector. So you get these sort of shark fins, where at low energy, there's thorium that contributes between this range for the neutrino energy. And then uranium contributes at low and then also has a second lobe at higher energies going out to 3 MeV in neutrino energy, 3.27 MeV. Okay. So, right. So then there are and were liquid scintillator detectors around the world. CamLand in Japan, Borexino, which was in operation, but now has concluded in Gran Sasso Lab in Italy. Snow Plus, the follow-up to Sudbury Neutrino Observatory in Canada. And the Juno experiment in China that has just come online. And so then we can see that around the world, the rate can be different because you're in a different location. But not only that there are nuclear reactors around the world. Actually, there are nuclear reactors in all these places that have neutrino detectors, which is good because we want to detect the reactor neutrinos too. But they are a background if your goal is to detect the geoneutrinos, right? And so anyway, nuclear reactors in Ontario, in Japan, China, in Europe. So then we have to understand this as a background too. Okay, so let me see here. I'm going to show you the CamLand and Borexino geoneutrino measurements as a sort of very flash, and then I'll tell you about what we're measuring, and then we'll come back to understand the geological interpretation of them, right? So CamLand was the first experiment to detect the geoneutrinos in 2005. CamLand was primarily an experiment to look for reactor neutrino oscillations, and then they saw them. But you can see that the expectation for the reactor neutrinos in the detector versus the geoneutrino is not so favorable for the geoneutrinos, but then they see this excess at low energy in the very first observation that was a cover of Nature in their Nature publication, and the total number of geoneutrinos they quantified was something like this, 25 plus or minus 18, 19. But then CamLand has continued to take data, and the most recent publication in 2022 shows 3 different periods. What happened in 2011 was the tsunami that led to the Fukushima nuclear meltdown. And then Japan turned off all nuclear reactors for several years. So then they have low reactor neutrino background for their geoneutrino measurement for several years. Now Japan has restored many of those nuclear reactors. But then in 3 different periods, where the initial period where it's kind of hard to pick out the geoneutrino signal, And then a period 2, I don't remember the details for what period 2 was, and period 3 where you have low reactor signal, then their combined analysis then sees, these number of geoneutrinos are detected. And over, a time span of some 14 live years of data. And then there's the geology interpretation that I'll come back to so that we'll look at them all together. Okay. Then in 2010, Borexino liquid scintillator detector was operating, and then they published their first detection of geoneutrinos. Borexino, much lower background, so a fantastic experiment with incredibly low backgrounds, lower backgrounds than CAMLAN, lower backgrounds than what we have in SNO+ too. And so their backgrounds are this, right? This little thing here. Whereas CAMLAN has a background that also I'll come back to. You can see that here they've got this background from alpha N, and I'll talk a lot about that later. And so we'll come back to it. So then CAMLAN has reactor neutrinos as a background to the geo, and this alpha N background I'll talk about later. But Borexino, also reactors are far from Italy. Italy doesn't have nuclear power. Closest reactors are in Slovenia, to Gran Sasso lab. So there are reactor neutrinos detected by Borexino, but then this is what they saw as their initial observation, about 10 geoneutrinos plus or minus 3, 4. And then Borexino published their final analysis in 2020, which this is what they saw. So then let's just step through this. Here are the reactor antineutrinos. So the nuclear reactors produce antineutrinos with higher energy above the endpoint for the geoneutrino. So then these are all reactor neutrinos. And then the geoneutrinos have this sort of double shark fin structure here. There are cosmogenic backgrounds in Borexino that are quite negligible, though. Accidental coincidences show up here. They have a very small alpha N background that they quantified in this analysis. Total number of, like, say, 50 plus or minus 9 geoneutrinos that they see over a time span of 8.7 live years. Borexino has been decommissioned, or they ended their run in 2021. So there won't be any more results, although CAMLAN is analyzing. They still have a final result. CAMLAN has also been turned off. They're upgrading to CAMLAN 2 in order to do a better double beta decay search with a CAMLAN detector. But they still have geoneutrino data in the pipeline that they'll eventually analyze and release. And then again, I'll hold the Borexino geology interpretation to the end. Okay, so then on to SNO+ then. So the original Sudbury Neutrino Observatory looked like this: 1,000 tons of heavy water in an acrylic vessel, 12-meter diameter, all of it located 2 kilometers underground in what's now called SNO Lab, right, in an active mine near Sudbury. Right, and then for SNO+, what we did was we replaced the heavy water with liquid scintillator. Because the scintillator is buoyant, it makes the acrylic vessel buoyant because the density is less than 1, and there's normal water around it. We installed this hold-down rope net to hold down the buoyant acrylic vessel, and then we changed the logo. Right. And so SNO+, we made this transition in the early, starting from 2012, converting this to a liquid scintillator detector, including all of these photos showing interesting operations inside the acrylic vessel, on top of the acrylic vessel, in boats to repair PMTs, upgrading electronics. Eventually, SNO+ was initially filled with water as we were installing a plant to purify liquid scintillator underground, installing a very complex chemical factory in the SNO Lab with kilometers of pipe and heat exchangers, vessels, pumps, and so on, in order to produce pure liquid scintillator that then fills the 780 tons inside the acrylic vessel. That's the original SNO acrylic vessel after the heavy water was removed. And so then SNO+ then has run in several phases. There's a water phase in which these are some measurements that we made. I won't spend time reading through this, but we made measurements with SNO+ filled with water, including some physics measurements that are world leading. Then as we started to fill the detector, not a bit off, this has been shifted a bit. Yeah, these timelines have been shifted a bit, I think. No, oh, no, it's fine. No, never mind. Sorry. Yeah, we started filling the detector just before in 2019, filling with scintillator, and then we encountered the pandemic that caused us to pause operations for 6 months or more. So we had a period of so-called partial fill where scintillator is floating on top of the water. And we even did physics during this phase. That's not the only publication that came from partial fill. And then since about 2022, we've been filled completely with scintillator, with low concentrations of PPO, with higher concentrations PPO, the fluor that goes in the liquid scintillator. Then now we've added a wavelength shifter, bismuth B, since 2023. And so we're doing physics in the scintillator phase with SNO+, neutrino physics. And that includes, we actually have an article that was accepted in PRL that will be featured in as an editor's suggestion in the upcoming week, I think. I won't talk about this at all, just other than to advertise that. It's the first time that charge current solar neutrinos have been detected using a charge current reaction off of carbon-13. Okay, and so PRL will do a little science outreach for us, but I won't talk about that because I'm going to return to the focus on the geoneutrinos and the antineutrinos. And then, but instead, today what I'll show you is our latest reactor and geoneutrino results that we're going to submit to PRL and the archive tomorrow. Okay, so you get to see this first. So here are the new results for reactor and geo antineutrinos from SNO+. Okay, yeah, okay. So reactors near SNO+. We have the Bruce, Pickering, and Darlington nuclear stations. They're about 240 kilometers and 350 kilometers away from Sudbury. And they provide about 60% of the reactor neutrino flux that we see. And nuclear reactors is the fission of uranium and plutonium that produce isotopes that then beta decay and emit antineutrinos, a copious number of antineutrinos per gigawatt thermal of the reactor. In order to model the number of neutrinos coming from a reactor, we have to track the power output from all of these reactors. And Ontario has the IESO, Independent Electricity Supply Organization, operator, IESO. And so then for each of these nuclear plants, you can see the hourly electricity output. So we can monitor the operational status of the Ontario reactors hourly. For US reactors, there's publicly available data for daily thermal power from the US NRC. And then the world's nuclear power reactors, which are included in the analysis, are updated in a database by IAEA monthly. Okay, so then we cross-check the monthly data from IAEA with our hourly and daily data for the US and Canadian reactors that are, of course, the important ones that are sending new bar towards SNO+. Of note is that near in Canada we have CANDU reactors, right? They're moderated with heavy water, and that gives rise to a slightly different neutrino energy spectrum. So that's of course in our models as well. CANDU reactors also are continuously refueled, resulting in what are called the fission fractions. How much of the energy being produced by the reactor comes from U-235, how much from plutonium-239, for example. They're approximately steady state values because of this trait. Okay. So what is the objective for measuring antineutrinos in SNO+? The reactor antineutrino oscillation measurement, the goal is actually to look at delta M squared, okay, the mass splitting. And there's an interesting observation is that delta M squared from CAMLAND, the CAMLAND experiment in Japan, measured the oscillation of neutrinos from reactors, had a preferred value that's a slightly higher value than the solar neutrino delta M squared. And there's no statistical tension here given the large error bars, right? It's not more than 1.9 sigma or something like that. But it's interesting because these are nu E bar from reactors, and these are nu E from the sun, including matter effects. So there's a whole host of new physics that one could introduce that could give rise to this being an actual difference. And so SNO+ would be only the second experiment to ever measure delta M squared 2-1 using reactor neutrinos. So we will also measure it with solar neutrinos as well. Okay, so then just so I can leave time for questions, I'll try to accelerate a little bit here. So we've analyzed two data sets. One from this period with this number of live days when we had our scintillator LEB plus PPO. Then later we had another 400 days where we added the wavelength tissue to BIS MSB. Total of 1.46 kiloton years of lifetime. In our analysis, we had two independent analyses, mostly independent, with two different oscillation parameter fitters that with independent frameworks as a cross-check. Our selection of events is trying to pick out these IBD events with the delayed coincidence. So cuts on the prompt and delayed energy, cuts on delta R and delta T for this coincidence. There's a likelihood ratio that rejects a few accidental backgrounds. We tag BIPO 214 from radon decays because it has a half-life that's similar to the neutron capture lifetime. So in periods when you have high radon in your detector, this can help you reject that. We veto after every muon, after every high-end hit event, multiplicity cut, all the details analysis. Because SNOLAB is so deep, SNO Plus only has 3 muons per hour, right? So then even a very aggressive veto cut only reduces the lifetime by about 2%. And then we end up with these number of IBD events. So from reactor, so and so then this column is the expected number from our models. This is the best fit from our result, which I'll show in the next slide. This one is the best fit, and we constrain the oscillation parameters, so targeting the geoneutrino measurement. And then this one, more on this one later, this column. Okay. So anyway, we classify our events that are IBD-like, and then this is the new result, and so that you're seeing it for the first time outside of SNO+. Okay, so here's a spectrum of here's our data. These are IBD events, so what we think are antineutrinos plus some background, right? And so here's the spectrum versus the prompt energy, right? So then nu bar plus proton makes the positron. This is the positron deposit energy, including the 2 annihilation gammas. And so it's a simple one-to-one relationship with the incoming neutrino energy, right? So then we can see the wiggles that come from neutrino oscillations. And we can see clearly the excess of events at low energy that are a measurement of the geoneutrinos. And so our fit finds something like 50 geoneutrino events in this that we can separate into the fit divides it into the thorium and the uranium components. And then there are background terms here. There's in particular this large background, alpha N. What is that? Okay. So the alpha N backgrounds, if you have an alpha decay, alphas can find carbon-13 in your detector. Only 1% of carbon is carbon-13. And then that produces oxygen-16 and a neutron. And what the neutron does is it recoils a bunch of protons. And then the neutron itself captures on hydrogen, it makes the delayed signal, right? So then the proton recoils makes a prompt event. And then this neutron capture makes a delayed event. And this makes a background that shows up here. Actually, it shows up in 3 places. These are the proton recoils. This is when the neutron excites 4.4 MeV in carbon. This is when the oxygen-16 that's produced is in an excited state and de-excites with 6 MeV, E plus or E minus or a gamma. Okay. And so then here's our fit. So this is the fit of the oscillation parameters. So we can see here is CAMLAN reactor in green. Here is SNO+ in blue. There's the solar neutrinos in this orange color, and there's our combined fit. Okay, so then the CAMLAN on its own measurement is like this. And then our measurement on its own is almost as good as the CAMLAN measurement. And then the combined fit, they're actually, the central values are a bit different. The combined fit, produces a smaller uncertainty. But we also extract the geoneutrino flux at SNO+, 2 different ways, and then I can explain what this one is coming up next. So how are we doing for time? I'm certainly into my question period here. But let me try to wrap up here. So these alpha N events, our postdoc built this tool, this classifier. Okay, so then recall what these are, that you get a prompt event from all of these proton recoils. and then you get the delayed neutron capture. Okay, but in a actual antineutrino interaction, IBD, you get a prompt positron with 2511 keV gammas, and you get the delayed event. Okay, so then this prompt looks different than this prompt, and why is that? It's because not only is the proton scintillation a slower scintillation, so the pulse shape is slower, but neutrons themselves are slow. Right? So as the neutron scatters multiple protons and bounces off of them, then you get a difference in the time residual. And so then our postdoc built a classifier based on a Fisher discriminant. Here's the ROC curve that then can efficiently cut these alpha N backgrounds while preserving the signal. And so then here's the plot where the alpha N classifier has been applied. So this is to be compared with this. So it's the same data set, only now these large alpha N backgrounds have been substantially reduced. And so then the geoneutrinos you still pick out. In fact, you make a better measurement. And so then that's the result that we will quote as our geoneutrino measurement is this one here, right? So this 49 plus or minus 13. Okay, so then now I'll have to blast through the geology to close it up. Okay, so when you make a measurement of the geoneutrinos, you have to subtract the local contribution because here's like a plot that shows the contribution from the crust and the mantle towards the signal at SNO+ is something like 80%, 20%. Right? So most of the flux is from the crust, but the crust is actually something that you can know very well because you can sample the rocks in the Earth's crust across the globe and determine what the uranium and thorium content is. So you really want to understand it thoroughly so you can subtract it. And doing so, you're trying to get at the deep Earth content that is the interesting one. And so then for SNO+, this has been studied in where there's been a campaign to study the geology near SNO+ through seismic data, through heat flow, through rock samples. And so our geology friends have done a thorough characterization for SNO+. And so then this figure is a little too hard to explain in no time. Let me jump to, so then, yeah, I've got these figures for SNO+, for Camelan and Borg. So let me jump to this easy one, and then I've got the summary. So, okay. So what I was trying to explain is that Camelan has measured the geoneutrinos over the years, so has Borg-Sino. And here's SNO+, our first result in 2024, a very preliminary measurement, and here's our new data point. Okay, so then what we want to know is that the contribution to the geoneutrinos, there's the crust that's close to the experiment that you want to thoroughly evaluate. Then there's the rest of the world crust that contributes. And then on top of that would be the mantle signal. Okay, and so then what we see is that in Camelan prefers that the mantle doesn't contribute very much, if you believe these data points. But Borg-Sino prefers that the mantle contributes a lot. And then we're currently here and to be evaluated what SNO+ believes to be the mantle contribution after we subtract our local crust contribution. So this notion that here we're actually doing a global analysis, right? By combining these results and the models. And so then in summary, that's what we did. We shined the spotlight on geoneutrinos and SNO+, and the newest results that that will be in our paper include improved precision on delta M squared 2.1 and geoneutrino flux measurement with precision. All right, thanks very much.
Thank you, Mark. That's great. Seeing a new result, or actually about to be new result, I guess. So, questions?
There.
Oh, yes.
Why do we have alpha particles in there? Yeah, so they're radon decays, and then once radon decays in your detector, it's not there, but it has lead-210 that is long-lived, 22-year half-life. Lead-210 decays into bismuth-210 and then polonium-210, which is an alpha decaying. And so then the radon exposure history, not just in Snow Plus, but also in original snow, built up lead-210 that then got released polonium-210 into the scintillator. So we have a relatively high amount of polonium-210 alpha decays in our scintillator that are the source of our alpha N background. Right? The Camelan also had, but Borksino didn't. They had a much lower background. That's right, during construction.
Yes.
How well is the angular resolution for geoneutrinos and related nodes? Is there any like cross correlation with Camelan or, for example, with the other neutrino, the other experiments you can pinpoint the actual source?
Right, good question. So the question is about angular resolution. Can you point back to where the Newey bars come from? The answer is you can't, right? It's very poor, if at all possible. So the scintillation is isotropic. The only thing that preserves the direction of the incoming neutrino is the displacement of the vertex between the neutrino interaction, meaning the positron scintillation, and then the neutron, because the kinematics push the neutron in the forward direction. So this provides a bit of angular correlation, but it requires events like 10,000 events in order to statistically extract this, because this gets randomized by the neutron walk. And then this also emits a 2.2 MeV gamma with a range of like 40 centimeters, right? So punishing to try to pick out this directionality theoretically can be done, and some experiments with high statistics have seen hints of it, but not for the geoneutrinos.
Other questions? Okay, well, yes, very good.
Yeah, so good question. So neutrino oscillations, how do we take that into account for the geoneutrinos? Because the neutrinos are a distributed source, right? Then one can do extensive calculations for it, and one finds that the average survival probability is sufficient to characterize the suppression of the geoneutrino detection. And so given the oscillation parameters that we have, that's something like 0.55. So for then, if there was a uranium mine close to your detector, right, that has a substantial quantity of this, that would be a substantial fraction of the signal you would see, then in principle, you'd want to get the distance, the baseline correct, and for the oscillations. But it turns out even the fact that Elliott Lake is close to Sudbury isn't enough of a concentration to make a difference. And then the global averaging in these calculations is at least as good as 1 or 2% in terms of the prediction. Yeah.
Okay. There's time for perhaps one last question. Okay, seeing none, let's thank Mark again.